A steel beam under a dynamic load bends continuously across its entire length. Every microscopic point along this span moves, accelerates, and deflects. This continuous motion is governed by a partial differential equation. Looking at the top of this document, we see the equation of motion for a beam. The density and area term represents inertial forces, and EI maps internal bending resistance. While this equation perfectly describes the physics of a simple, uniform beam, trying to solve it analytically for a complex, multi-part real-world structure is impossible. There are simply too many variables across continuous space. To actually engineer structures, we have to perform a mathematical translation. We must convert this infinite continuous domain into a finite, discrete mathematical system. The destination for that translation is this discrete matrix equation. It breaks the physics down into three distinct arrays: a mass matrix multiplying nodal accelerations, a stiffness matrix multiplying nodal displacements, and a generalized force vector on the right side of the equal sign. This specific linear algebra format is the native language of computational solvers. Computers cannot process infinite continuous calculus, but they can rapidly multiply large matrices. We are going to walk step by step through the mathematical derivation that bridges these two worlds, generating these exact finite element matrices from the original physics. Structural engineering software relies entirely on this sequence. It takes unsolvable continuous mechanics and reformats it into solvable discrete algebra. Our derivation begins with the reduced form of the energy equation. Looking at this integral derived from Hamilton's principle, we see the total energy balance. Inside the bracket, the inertia term resists acceleration, and the EI stiffness term determines resistance to curvature. Finally, external work from loads balances the internal energy. The mathematical bottleneck here is the variable v, the continuous displacement function. We cannot execute this spatial integration because we do not know the true physical shape the beam will take under load. To bypass this block, we have to construct an approximation of the displacement. Since the continuous curve is unknown, we slice the beam into discrete nodes and mathematically dictate the behavior between them. This is done using interpolation functions, often called shape functions. These are predefined mathematical rules that connect our discrete nodal points. For a beam, we use cubic polynomials. This document shows the derivatives of these shape functions, n' and n double prime. They map the discrete nodal displacements to any continuous position, with the second derivative giving us the internal bending strain. A parallel relationship exists for the time derivative, linking these same shape functions to the element's nodal accelerations. Geometrically, a cubic shape function acts as a rigid guide. It forces the physical material to form a smooth curve between two distinct nodes, while exactly matching the required slopes at the boundaries. By defining the geometry with these functions, we successfully separate the spatial variables from the time-dependent motion. These shape functions define the element's interpolation space, establishing the rigid geometric constraints that dictate how the segment is physically allowed to deform. Now we execute the core mathematical substitution, plugging our new shape functions directly into the energy integral. Looking at the resulting equation, the complex partial derivatives are replaced by our vector formulas. We group all the spatial variables strictly together inside the spatial integral. This allows a critical factorization, pulling the time-dependent nodal vectors completely out of the integration boundary. Once those time variables are safely outside, we execute the spatial integration across the length of the element, dx. The complex polynomial vectors evaluate out, collapsing into fixed, constant numerical arrays. The generalized force vector undergoes a similar process, though its final numerical values depend entirely on integrating the specific applied load profile against the shape functions. With the spatial integration finalized, the original continuous calculus problem has been reduced to a discrete algebraic matrix. This document reveals the fully integrated 4x4 mass and stiffness matrices for a standard beam. The mass matrices' scalar coefficient, density, area, and length over 420, results from integrating the shape functions. Likewise, the stiffness matrices coefficient stems from second derivative shape functions and physical rigidity. These exact matrices are powerful, but they have a strict limitation. They only describe one isolated piece of a beam. To analyze a real structure, we have to perform structural assembly. Elements must be joined together at common nodes. The first law of this assembly is geometric. The displacement and slope at the end of the first element must perfectly match the beginning of the second element to ensure the material remains physically continuous. The second law is static equilibrium. Any applied concentrated load at that shared node must be divided properly among the connecting elements. To satisfy these laws, the individual 4x4 elemental matrices are mathematically overlapped at their shared nodes, adding together to form massive global structural matrices for the entire object. Finite element solvers automate this entire sequence, generating elemental matrices from shape functions and assembling them into global systems to predict the mechanical response of structures with millions of degrees of freedom.